Hey guys, this is 18.4 neutralization. When you finish watching today's video, you should know what neutralization reactions are, you should know how a titration works, and how to choose the correct acid-base indicator to have a successful titration. You also should know what buffer solutions are. Well, a neutralization reaction is a reaction where an acid and a base in an aqueous solution react to produce a salt and water. This is always a double replacement reaction. Salts are considered your ionic compounds that are made up of a cation and an anion from an acid. Now this does not have to be NaCl. It can be any metal with any nonmetal. That's your cation and your anion. So this is just any salt, magnesium chloride for instance, or magnesium sulfide, that all would work as a salt plus your water. Now we're going to talk about titrations. This is very important because you are going to perform a 2-day lab experiment where you are going to titrate an acid and a base. A titration is a method for determining the concentration of a solution by reacting a known volume of that solution with a solution of known concentration. There are 3 steps to the procedure that you're going to follow to find a titration. First, you're going to place a measured volume of an acid or a base solution of unknown concentration in a beaker. Instead of using a beaker, we're going to use an Erlenmeyer flask. Then you're going to use a pH meter to read and record the initial pH of the solution, or you could add an acid-base indicator. We are going to use the method where we add an acid-base indicator. The second step is you're going to fill a burette with a titrating solution of the known concentration. Now, the burette is your long, skinny measuring device. It's very accurate because it's so skinny. It's going to have its lines between milliliters very distinct, and you're going to be able to read very accurately the volume of the solution that you're adding into the Erlenmeyer flask. This is a standard solution, or the titrant. Now we're going to be referring to that as our titrant. The third point is the most important part of your process. You have to slowly add and mix the measured volumes of the titrant to the beaker, or the Erlenmeyer flask. As you are doing this, what we're going to look for is a color change in our Erlenmeyer flask. When you're doing this, if you're not doing a color change, we're going to measure and record the pH after each addition. So you're going to start by adding maybe 5 milliliters at a time. And then you're going to lower that to maybe 2 or 1 milliliter, and then eventually you get down to drop by drop adding the solution, the titrant, into the Erlenmeyer flask. This process will continue until you reach the equivalence point, and that's a really important term to know. The equivalence point is the point where the moles of your hydrogen ions from the acid equal the moles of the hydroxide ions from the base. And the whole point of doing our titration is so that we can find the moles of the unknown base, or the unknown acid. So that is why we do this process, to reach that place where they are equal to each other. The equivalence points can also be found by using your acid-base indicator, and that's the one that we're going to do. Instead of taking the pH reading after each addition, we're going to use an indicator. The equivalence points are reached at a certain pH, and the acid-base indicator is going to be chosen so that the color change happens exactly at that pH where the equivalence point is reached. So an acid-base indicator is going to be the chemical dye whose colors are affected by the acid and the basic solutions. Now there are many different pH indicators, or acid-base indicators. Notice that this chart has methyl violet all the way down to Algerian yellow. Now each and every one of these different indicators has a color change for a different pH range. Notice that the first one is going to change between 0, where it's yellow, to just above 1 pH. It's going to be a purple color, or a violet color. The thymol blue starts as red with a pH of 1, and then once it crosses that pH level of 2, it'll change to yellow. So notice that for each and every one of these, we're going to have a separate pH where when it changes color, we know what pH it just was. The one that we're going to use in our lab experiment is going to be phenolphthalein. That's the third one from the bottom. If you notice, phenolphthalein is colorless to start, so it doesn't have a color at around the range of 7 pH. Once it crosses over to 8 or 9, it changes to a red. But what we want is the very first change around the 8 pH of 8, where it goes from being colorless to being very pale pink, because that is where we have our equivalence point. The end point is the point at which the titration changes color, and so that's when you stop your titration. You want to choose the indicator for a titration that will change color at the equivalence point of the titration, and the color change should let you know that there was just enough of the titrating solution added to reach that equivalent point, the point where the moles of the H are the same as the moles of the OH. So notice that when you add your liquid, you're going to see spots of pink showing up from your titrant being added to your solution, and it's going to disappear and go back to colorless. Right when that color is established and does not disappear again, that's when you've reached your titration endpoint. And that's where you really want to be careful, because you want to make sure that that is the palest pink that you can get. Otherwise you added too many moles of the H or the OH. That brings us to our last point, the buffered solutions. Buffers are solutions that resist changes in pH when limited amounts of acids or bases are added. Now this is important. It's very limited with the amount that you can add. You can't just add an entire gallon of acid to a buffered solution and expect it to be able to hold up its end of the bargain. The way that we create a buffered solution is we have mixtures of a weak acid and its conjugate base, or you can have a mixture of a weak base and its conjugate acid. This mixture will resist changes in the pH by reacting with any extra hydrogen ions or any extra hydroxide ions that are added to the solution. Now, these are going to work by obeying the Le Chatelier principle. Remember, if we add concentration, it'll shift left or right because it's going to shift away from where that concentration was added. So this will help our buffer solution whenever we add OH or whenever we add H, it'll shift away from that and it'll shift to make more concentration of either the acid originally or the base originally so that you stay with the overall pH being the same. So it kind of is a self-regulating system. Now that does bring us to the last point that we're going to learn about, which is our buffer capacity. Now remember, if you think of a capacity of a land, that's going to be the maximum amount of animals that can be supported on that land based on the amount of food that's provided or the land, the room for territory and things like that. This is the maximum range that your buffer can establish and still keep the pH the same. It's the amount of acid or base that the buffer can absorb without a significant change in your pH. And every single one of your buffered solutions is going to have a different buffer capacity, and if you're in this situation, you have to actually research which capacity you have so you choose the correct buffered solution for your job. Now that you've finished watching today's video, you should know what a neutralization reaction is, how a titration works, and how to choose the correct acid-base indicator for that titration, and what a buffered solution is.